Hi everyone, welcome to today's webinar. My name is Ryan and I work here at DataCamp on the marketing team. Today's webinar guest is Hugo Baun-Andersen, a data scientist at DataCamp. Hugo graduated his undergrad as a double math major and later got his PhD in pure mathematics at the University of New South Wales in Australia. He later worked in applied math research and cell biology at Yale University and the Max Planck Institute. He joined DataCamp a couple of years ago as a Python curriculum engineer and is now the host of Data Framed, the DataCamp podcast. Check out the podcast if you haven't already. And now, Hugo will give a presentation on data literacy in the 21st century, followed by a Q&A. Hugo, take it away.
Hey, thanks, Ryan, and thanks for everyone here in-house at DataCamp who is instrumental in putting these webinars together, such as Ryan himself and Gabriel Deselding, another colleague of mine. And thank you all for joining today. I'm really excited to be here to talk to you about data literacy in the 21st century and what I feel and what we feel at DataCamp are the things that we all need to get better at learning and working with respect to data. As Ryan mentioned, I'm Hugo Baun-Andersen. I've been here at DataCamp for several years. You can get in touch with me best way probably on Twitter at Hugo Baun. You can follow DataCamp at DataCamp as well. As Ryan mentioned, we'll have a Q&A afterwards. So if you have any questions that arise throughout, type them into the GoToWebinar interface as soon as they come to mind, and we'll be able to then go through them while I'm talking and have them ready to go after the fact. So without further ado, I'd like to open by just telling you a bit about what I hope you can get out of this talk. And there's Homer Simpson thinking for good measure. I'm not sure if that's me or you currently, but we'll find out after the fact. So the first thing I want you to get out of this talk, it really is how data science affects our lives. Then how we as data scientists actually think about data, because I think that people in general may not realize kind of how we look at data, the smell of it, the taste of it, and how we think about it. And then I want to develop working definitions and intuition for artificial intelligence, AI, machine learning as well, and deep learning, along with a few other things. But these are kind of the key takeaways that I want you to get out of this webinar. So firstly, let's just try to get like a working definition for this nebulous term of data science. So what is data science? I really like Thomas Davenport and DJ Patel's definition of what data scientists do. It's people who make discoveries while swimming in data. And the way I like to think about that, swimming is such a good term for that, because swimming, I suppose, is you're surrounded by water. It can be quite overwhelming, and it's similar when working with data. And the advent of data science as kind of a burgeoning nascent discipline came with kind of the large amounts. It kind of came after the big data revolution. We realized we had all this data to work with of various forms, and suddenly we're swimming in it. I also want to kind of have a definition from Wikipedia that I like a lot. And I've highlighted the key terms here, that it's interdisciplinary. Data science draws on a lot of different disciplines. It uses scientific methods, processes algorithms, and it deals with data in various forms. So as we'll see, there's structured data that we can put in tables, like in spreadsheets. There's visual vision data, which we can represent as grids, and there's unstructured data such as HTML code and text. And a lot of working data scientists will draw on all different types of data in order to answer their data scientific questions. Okay, so when we talk about data science, I want to motivate it first by talking about why you should care about data science. Then I'm going to talk about what it actually is. We'll go a bit further into that. Then I'm going to talk about kind of the smell of data, or the feel of data, or how data scientists work with data and what they experience. Then a few things about statistical intuition. And then we'll go into models, machine learning, and AI. And what we'll do then, as I think is very important, we'll wrap up with a conversation around data ethics. Now, except for the introduction here, why you should care, I think these 5 sections of what data science is, what data feels like, statistical intuition, models, ML and AI, and data ethics are kind of the 5 buckets that I think the 21st century citizen needs to know about in order to have educated conversation around data. And I'll also mention that this talk has a lot more in it, but it draws on a series of articles I'm writing for Harvard Business Review that you can check out. The first one's out, and you can check it out by Googling my name and HBR. And essentially, and feel free to reach out with feedback as well. So without further ado, why should we even care about data science? There are three main reasons we should care. The first is that it will affect your job if it doesn't already, and your entire industry. The second is that it's a personal reason. There's a lot of data that is yours and is mine, and figuring out this idea of data ownership and what's happening with it in the world and how it then impacts our lives. Everything down from push notifications to our health records being shared. The final thing is for us to have educated conversations about the world, such as election polling and forecasting. We need to have a better kind of I suppose cultural and shared cultural idea of what data is, what statistics is, and all of these types of things. So let's look at your job to begin with. You need to be part of the conversation in the workplace, whether you're a data scientist or not, because so much data is informing decisions across so many industries. You just need to have a basic understanding of the ecosystem to be part of the conversation. And on top of this, if it hasn't been already, the industry that you work in will more likely than not see the impact of analytics. And I just want to take you through a few examples. I mean, it's across the board, but let's look at healthcare. Okay, so instead of diagnoses being done by humans looking at imaging data, we now have high throughput systems of disease diagnosis that outperform the experts. So two examples are MRI and PET scans. One example I like to discuss is that Google AI have developed an algorithm to detect diabetic retinopathy as well as the expert scan. And to put this in context, this is one of the leading causes of blindness globally, and around 400 million people have this disorder. On top of this, Google AI has done this in collaboration with health and biomedical researchers. But I want to make it clear, if it isn't already, that Google isn't necessarily in the business of healthcare, right? That isn't their main objective. So it's interesting that tech companies are actually coming up and using their data science, machine learning, and AI chops in order to solve problems outside of their specific domain. And that's something we're going to see a lot more of. Even think of the capabilities of biometric sensors in Apple Watches and all of these types of things. Okay. Then agriculture is really interesting. The ability to analyze satellite or drone imagery to predict crop yield. And I'll urge you all to check out a startup in India called Farm Guide that does this type of stuff. They do a lot of interesting work, but that takes a lot of manual labor out of the equation. And also notice that in these examples, we're not, and I'll get to this, we're not talking about automating jobs, right? We're talking about automating tasks. And what I mean by that, nobody, doctors won't lose jobs by having high throughput systems to make disease diagnoses, but it will take out a bunch of their work so they can focus perhaps on the more human aspect of their job also. So I want to make that very clear. And then legal tech is something which is, it's really, I think, not a huge part of the conversation at the moment, but it's a huge, it's a 16 billion, legal tech is a $16 billion industry in the US. You can imagine that a lot of the work in law is drafting, reviewing, categorizing, and we now have a whole bunch of natural language processing and natural language understanding techniques of analyzing textual data that can do a lot of this work as well. Now, what is AI? So all these things we've been talking about, being able to categorize or predict rulings or analyze images and diagnose diseases, all of this is essentially under the umbrella term AI. And I just want to make clear that AI is, if this is possible, an even more nebulous term than data science. And it's essentially a catch-all that refers to generally creating systems capable of making intelligent decisions. And that's what we've been talking about. All these use cases I've just gone through fall under the umbrella AI. Okay. Now, what it isn't, AI is not AGI. It is not artificial general intelligence. That's what we think about when we think about, sentient computational beings that have their own ethical systems and can, write their own Bibles or whatever we see. And why I use that example is because check this out. Late last year, there was a headline. We see these headlines all the time. An AI God will emerge by 2042 and write its own Bible. Will you worship it? So that's a nonsense. I don't even know if that question follows from the statement that precedes it, but I love this because it shows that how ridiculous a lot of the conversation around AI can be. And what I want to do here, and part of our project at DataCamp, is essentially to demystify these types of things and show what AI is capable of, what its limitations are, and where it's most appropriately used. So when we think about AI, let's think about algorithms that will diagnose disease, for example, or look at a legal document and predict what the ruling may be, and maybe doesn't do both of those tasks together. Specialized AI essentially. So I want to make that startlingly clear. Okay. One final word about automation and job loss. This is a World Development Report 2019. I don't know how they did the 2019 one yet, but no, that's just a poor joke. And we see here, let me just find, fears that robots will take away jobs from people have dominated the discussion over the future of work. But this report seems to think that more jobs will be created, and there's a lot of research happening around this currently with respect to that. And I'd just like to mention once again that a lot of the time, there are industries which we really need to think hard about in terms of job loss, but a lot of the conversation also needs to be around task automation and not job automation. And I urge you all to check out this report this year or next. Okay, so once again, why should you care about data science? The next reason is it's your data. Whenever you go on the web or interact with apps, whether it be WhatsApp, Instagram, Google, Facebook, data is being collected about you, and we all need to be aware of this and the potential repercussions. So not only that, but the Internet of Things, whether it be Alexa or Roomba or a Fitbit or your smart fridge, any of these things. And we're going to see a lot more objects and things being connected to the internet in the coming years, and all of these will be collecting data about us. They also provide really incredible welcome services, and that's why we use them, right? But we need to be having a conversation around this more. So what do we need to know? And I don't have all the answers here. Pardon me. I'd personally like to know what data is collected about me, by whom, why it's collected, how it's collected, and if it's mine anymore. So if I upload photos to a service, do they have some sort of intellectual property rights over it in some ways, okay? And also my legal rights. For example, the General Data Protection Regulation, which came into effect, I think in May this year in Europe. So these are the types of things we need to be talking about more. And just for example, this was the other day in the New York Times. New York Times had a huge expose of the type of data that's collected on us. Has some beautiful interactive graphics, which I urge you to check out. But they really dive into the fact that we're told data's anonymous, but anonymization is a perverse art at best, and it's incredibly difficult to ensure anonymization. And the data that the New York Times found really shows how personal a lot of the data is. Similarly, if you don't know, I grew up in Australia, in Sydney, and I was back in Sydney recently, and this was a headline last month: councils prying to residents' metadata to chase down fines. Also in Australia currently, there's a conversation around My Health Record, which what that will be is for any Australian citizen getting all of their health data in one place, and different medical professionals and otherwise having access to that. And a lot of people are fearful of this, but if you start looking into it, there are privacy and security controls. And I think in terms of thinking about our data, it's just so important for us as citizens to start, recognizing what our rights are and what they aren't. Even in terms of, controlling access to specific documents to limit who can view them, right? Now, finally, caring about data science because it's a way of discussing our world, and it's a very legitimate, effective, and informative way of talking about what happens in our world. one example which I love, and you can hear a conversation about this on an episode of the Data Frame podcast an interview I had with Julia Silge of Stack Overflow fame. She wrote this piece with the wonderful people at The Pudding called She Giggles, He Gallops, and they analyzed gender tropes in films with screen direction from 2000 scripts. And so what they discovered there, using data science and data analytics and data analysis, is that a lot of the time she will be followed by giggles in Hollywood scripts, and he will be followed by gallops. And presumably this is historic, perhaps from the Western movies. But we actually see that women will be followed by snuggles, giggles, squeals, sobs, weeps, blushes. Men will be followed by straps, gallops, shot, howls, kills, vaults, rears, etc. So suddenly we've already, discovered something about our world through data science and data and analysis. The other example that I heralded at the start is the news cycle and election polling and how polls are actually reported. Okay, so for example, 538, highly reputable pollsters in 2016 gave Clinton around a 71% chance of winning and Trump a 28% chance of winning. Okay, and this is, you can listen to this in the podcast when I spoke with Alan Downey, but this is something Alan has written about a lot. And so according to this model, Trump winning was actually more likely than flipping 2 coins and getting 2 heads, which has a 25% chance. And if you flip 2 coins and got 2 heads, I don't think you'd be all that surprised. Okay, so in terms of this prediction, we shouldn't have been that surprised that Trump won, right? It gets worse though. Various pollsters predicted that Secretary Clinton would win with probabilities ranging from 70 to 95%. And it was common to speak of these predictions as though all experts agreed Clinton would win, with different levels of certainty. What that does though, that makes it seem like these are deterministic predictions. And what I mean by that, they're saying Clinton will win and I'm this certain, as opposed to probabilistic predictions, which is Clinton has a 70% chance of winning. Okay. And so think about it like this. Even if an event is only 10% likely, that's about as likely as flipping 3 coins and getting all heads, which we also wouldn't find that surprising. So this is a huge problem that we haven't really had a conversation around what even these predictions mean. And this is an image generated by the MIT Nightmare Machine pre-election 2016, and it uses actually deep learning techniques to generate such images. But that's truly horrifying. So let's move on. This year, though, in November, the pollsters got a lot better. And so, for example, 538 were reporting that for the House forecast, the Democrats had a 7 in 8 chance, as opposed to giving a percentage, because there's been a lot of research into the fact that us as humans are far better at interpreting ratios than percentages, fractions than percentages. So that's fantastic. And Nate Silver actually is being very explicit around it. So he wrote, this is the point at which you might expect us to give, well, actually, about how 1 in 7 chances happen all the time, and they actually do. So 1 in 7 days of the week is Thursday, is that point. And so what he says is that nobody should actually be that surprised if Democrats win the Senate or Republicans keep the House. So if you have a 1 in 7 chance, it's not that surprising for something to happen if there's a 1 in 7 chance, right? So these are the types of conversations I'd like to see us having more and more. So before we really dive into the nuts and bolts of data science, I just want to present a model for thinking about technological innovation known as the Gartner hype cycle, where we have, as a function of time, we look at the expectations of any given technological innovation. So we have an innovation trigger. Then we have a lot of expectations, so the peak of inflated expectations, the trough of disillusionment, the slope of enlightenment, and then the plateau of productivity. Okay, so I'm just going to give you 10 seconds to think about where you think data science would be in this Gartner hype cycle currently. Okay. And if you're in a room with someone, tell them and have them tell you where they think it is. Just having a sip of my tea while we're waiting. It's delicious antioxidant green tea. Okay. So I'm not going to answer this directly. Straight away, what I am going to do is first say, a model for thinking about where big data is in the Gartner hype cycle. Now, how do we we can do time on the x-axis. On the y-axis, we have expectations. How can we think about expectations? How can we measure it? One proxy is just looking at Google Trends, okay? And that's what I've done here. And you'll see that, around 2014, there was a peak. So this could be the peak of inflated expectations. And then big data, we started entering the trough of disillusionment. So let's now plot big data, Google Trends with data science there, okay? Fantastic. So big data in blue, data science in red. And you can see that data science hasn't even reached a peak yet, actually. So for what that's worth, if we accept the Gartner hype cycle as a good model for expectations around technological innovation, and if we accept Google search results as a proxy for societal expectations, we'll see that we haven't actually reached this peak of inflated expectations yet. And of course, that isn't to say that a lot of value isn't being generated. All it is to say is that we'll see a lot more in future, perhaps after a so-called trough of disillusionment. So now let's get into data science. What is data science? So I had Cathy O'Neil, the author of Weapons of Math Destruction, and doing data science on Data Framed recently, and that was our finale episode of 2018, season 1. Okay. So Cathy in 2013 said that a data scientist is a data savvy, quantitatively minded coding literate problem solver. When I spoke to her about this definition, she actually said she's changed her definition recently to data science doesn't just predict the future, it causes the future. And what she means by that is that it actually has a strong effect. The models that are put into production, whether they're making recommendations for what you want to watch on the BBC, or models that predict recidivism and have an impact on parole hearings. We have a lot of data science models in production that actually heavily impact the future. Don't just predict it, because decisions are made based on these algorithms. Okay. So in terms of what data scientists actually do, today's data scientists there's a lot of data collection and cleaning. There's a lot of building dashboards and reports. They can do data visualization, building models, whether that be statistical models or machine learning models. And we'll get to what machine learning really means soon. And they communicate results to stakeholders. And after this, business decisions are then made. And any individual data scientist may not do all of these things. You may be a data scientist that specializes in data viz, for example. Okay. I'll just remind you, if you have any questions, please put them in GoToWebinar now, so that I can answer them after I wrap up the presentation. Okay. Data scientists do so much cleaning that Big Data Borat said, in data science, 80% of time spent prepared data, 20% of time spent complain about need for prepared data. And this is a joke on the trope that data scientists say 80% of the time is preparing data and 20% is building models. So the last thing I want to say about what data science is that, I've just showed you a list of all the stuff data scientists do. Data science is not just AI and deep learning. And Monica Rigatti built this beautiful AI hierarchy of needs. I think this is so relevant because a lot of people come and say to me, Hugo, I have this business and I want to build out AI capabilities. And I can then show them this and show them that AI is at the top of a very serious and complex hierarchy of needs, where you need to collect your data first. You need instrumentation, logging, sensors, external data, user-generated content, or a subset of these things. You need to be able to move and store it. You need to be able to explore and transform it. Only then can you start doing basic statistics and analytics and aggregation. And then you can start doing online experimentation and simple machine learning algorithms. And after that, you get to AI and deep learning. Okay? So I really think this is a valuable framework for thinking about how to build out data science and AI capabilities in any organization. And finally, in the first episode of Data Framed, I was talking about with Hilary Mason about what data scientists do and what they don't. And I asked what the biggest challenges Hilary thinks we face. She said, do you think that imprecise ethics, no standards of practice, and a lack of consistent vocabulary are not enough challenges for us today? And these are the types of things we're up against, which I'll come back to later, but it is still a very nascent burgeoning field. So now let's talk about the smell of data, what it looks like to data scientists. So what types of data do data scientists generally work with? Pardon me. So data, before I started working data science, I had a feeling that data kind of looked like this like streaming cascade tube cylinder of zeros and ones, and that is as far from the truth as possible. The general types of data that data scientists work with are tabular data, and so that's really a table, looks like a spreadsheet essentially. Image data, which we'll get to, and unstructured data such as HTML code and text, right? So tabular data, as I said, is analogous to a spreadsheet. This is from a beautiful post by Robert Chang about using ML to predict values of homes on Airbnb. And we'll see that each row is a property, and each column is a feature of that property. And that's how we put data in a table. The features are the ID of the listing, then the location, average nightly price, and so forth. And in the end, Robert Chang is thinking about predicting the value. And so this is essentially, he'd like to build an algorithm which will predict this column from these, and using machine learning to do that. And we'll get to what that really means in a minute. Okay. So then there's imaging data. Okay. Now, imaging data is used, the ability to diagnose disease from imaging data, as we've talked about. It's also used for facial recognition, which we all know very, very well these days. I mean, it's incredible that when I get my new iPhone or whatever I use, I can, take 3 photos of my face and it knows mine compared to everyone else's from then. So this is imaging data that data science and machine learning algorithms are using to recognize. Similarly, the ability of self-driving cars to detect and classify objects in their field of vision. Now, image data scientists don't really think about as we see images. What a data scientist will do is convert an image into a grid, otherwise known as a matrix, of red, green, blue pixel values or numbers, and use these matrices or matrices as input to the predictive models. Okay. So next, and wrapping up, we have unstructured data, such as natural language and HTML code. This is an example. I very much apologize. There's a couple of cuss words here, but that's due to the fact that it's Biggie Smalls' Notorious B.I.G. And I did use rap for a reason, and we'll get to that. But unstructured data, such as plain text or HTML code, if you want to scrape web pages and then figure out what's happening there, or compare it to other web pages, or classify web pages, we've got all of this unstructured data that we need to turn into structured data somehow. And natural language processing, the job is to give structure to it and to predict certain things about the data, such as you can imagine scraping a whole bunch of Wikipedia pages and trying to cluster them according to a topic. You can think about whether it's positive or negative, sentiment analysis, and once again, text classification. And one of the common natural language processing models is called bag of words. So that's why I've got a photo of a bag of words there. Okay, the reason I used rap, this is another example from the pudding. This is a beautiful piece by Matt Daniels, who I think was one of the founders of the pudding, looking at the number of unique words used by rappers, right? Used in their first 35,000 lyrics, which is really cool. And compared to Shakespeare and Melville's Moby Dick as well. One thing that I find interesting, there's a lot of stuff you can kind of tease out here, but one thing I find interesting is you've got a whole bunch of the Wu-Tang Clan clustered up here, which is pretty cool. Not only them together, but as individuals, you see that they're all relatively similar in terms of number of unique words used, which is pretty interesting. And there's, of course, it's interactive. There's even a button, just Wu. Cool. Okay, so the next thing I wanted to talk about, and I kind of heralded this earlier, is statistical intuition, because I think humans demonstrably are really bad at statistics. Okay, so to demonstrate this, I just want us to do a little thought experiment. So let's say police have breathalyzers that have a 5% false positive rate. That means that if someone isn't drunk 5% of the time, it will say they are drunk. Okay, and a 0% false negative rate. So that means if they are drunk, it will always say that they're drunk. Okay, and we also know that in society, 1 in 1,000 drivers are actually driving drunk. So my question is, if the police stop a driver at random and the test is positive, what is the probability that the driver is actually drunk? Okay. Now I just want you to think about it. Turn the person next to you, if there's someone there, tell them, or even better, ask them so that they have to tell you. What does your intuition say as to what is the probability that the driver is actually drunk? Okay. So I'll give you 10 seconds there. I don't want you to think about it. I want your intuition, because we're talking about intuition here. Okay. Now, most people in the studies that have been done, time and time again, this is some of reproducible science, right? In the studies that have been done, most people will say, at least 80%. A lot of people will say 90, 95%. Some people will say even more than 95%. Now, the real answer is that it's less than 2% probability that the driver is actually drunk, okay? Now, that may seem crazy, but the reason, and this is called the base rate fallacy, the reason is that generally our intuition looks at the 5% and forgets that only 1 in 1,000 are driving drunk. So we have this base rate that even at the outset, it's very unlikely they're drunk. Then we get a bit of more information that the test is positive, but we neglect this base rate, okay? So let's go through it. So imagine we do this 1,000 times, okay? Or a policeman does this with 1,000 citizens. So because 1 in 1,000 are actually driving drunk, out of this 1,000, on average, 999 people will not be drunk, but due to the false positives, around 50, there's a 5% false positive rate, around 50 will test positive, okay? Now, one person will actually be drunk. We've got a 0% false negative rate, so they'll test positive. So out of these 1,000 people, there are 51 people who, just let me get this right, I'm sorry. Yeah, 51 people who test positive, but only one of them was actually drunk. So this is less than 2% of the positive test results being true positives. So this is known as the base rate fallacy. And this is just to demonstrate how bad at statistics we actually are intuitively. And it's a data scientist's job and statistician's job to correct these types of heuristics and biases within organizations and society at large. I'm going to skip over Simpson's paradox for a matter of time, but I do want to tell you about selection bias, which is a beautiful example of how bad we are at statistics. So during World War II, Allied bombers were returning with damage all in the same place, but some weren't returning. And the question was, where do we reinforce these planes to make sure that more planes return? And we can see all these red dots where the damage was, and all the experts at the time said we need to reinforce the planes where the damage is, okay? Now, Abraham Vold, a statistician at the time, said, no, you're completely wrong. We need to reinforce the planes where the damage isn't, okay? And the reason he stated that is because the damage on the planes was only the planes that returned. And he realized that the other planes, if we presume that, planes will be hit uniformly, the other planes that went down would have most surely been hit in the other places, and that's why they went down. So they reinforced the planes then in the places where the planes that returning hadn't been hit, and saw more planes come back. So that's known as selection bias or survivor bias, because we're only looking at the survivors. So the ones that were hit in that region were the survivors, essentially, so that those regions are fine to be hit in, to labor the point. Thinking about these types of heuristics, biases, and statistical intuition, for further reading, I urge you to check out the work of Daniel Kahneman and Amos Tversky. Thinking Fast and Slow is a beautiful book about these types of things. For example, so now we get to the meat of it, right? We get to models, machine learning, and artificial intelligence. So what the heck is machine learning? I like to think of it as the science and art of giving computers the ability to learn, to make decisions from data without being explicitly programmed. So for example, saying some software that says whether an email is spam or not. That's known as supervised learning, because we're trying to predict a certain label, spam or not. There's also text clustering, which is unsupervised. And what that means is that we're not trying to predict something. We're just trying to look for patterns within the data itself. Okay. So a bit about unsupervised learning. It's the machine learning task of uncovering hidden patterns and structure. So we could cluster texts, we can cluster customers on a website, we can cluster genes in terms of whether they have an effect on one another. So this is just a small example of clustering users of a website. On the x-axis, we have hours spent per week, and y-axis money spent. These are two things that are of a lot of interest to the website. Money spent, arguably more, but we see that we can cluster these according to this cluster, and that cluster. If you wanted two clusters, maybe you just get that one. But this is kind of a toy example of thinking about segmenting users using unsupervised learning clustering in this case. We also have hierarchical clustering, which is really cool because at different, this is a visualization called a dendrogram, and at different levels we have different clustering. So if I look at the 15 level, I'll see these three are clustered, etc. And I hope you can see my cursor there, but if not, that's also cool. And one thing I just want to note is that this is countries clustered by Eurovision voting in 2016. And you actually see that what emerges are clusters of countries that have, either close geographical, social, or political ties. Serbia, Croatia, Slovenia, Macedonia, etc. And yeah, Sweden, Finland, for example, Poland, Austria, Germany. That Georgia, Belarus, Ukraine, Soviet Republic, and so forth. Another example of this is clustering of stock movements, and once again we see certain things emerge, such as American Express, Goldman Sachs, and Wells Fargo, Bank of America, JP Morgan, all together. And somewhere, if you can find it, we'll see a lot of tech companies. Microsoft, Yahoo, Amazon, Google, Alphabet. So clustering is a very important part of machine learning in the guise of unsupervised learning. But the lion's share of machine learning is actually supervised learning. As we discussed, predicting a diagnosis based on imaging, or whether an email is spam or not. So it's making, or the value of a property, or an action a customer will take. So making a prediction, and essentially one of the big wins for us that supervised learning achieves is being able to automate a time-consuming or expensive manual task, such as diagnosis, or to make predictions about the future, such as saying whether a customer will click on an ad or not. So let's just think a bit more, go slightly into the weeds of supervised learning. And so one very important example for a lot of businesses is whether a customer will churn or not. That means whether they will leave your business at any point. This is one example of a telecommunications network where each row is a customer, and each column is a feature of them, so we know their state, the state they live in, total number of evening calls, do they have voicemail, total number of day calls, and we know whether they churn or not. So what we want to do is we want to build an algorithm that will predict whether they will churn or not based on any of these. So what we need to give the algorithm data which is labeled, and what that means is data that says whether they churn or not, in order to then predict later on whether they will churn or not, if we don't know whether they will or not. And I'll speak more about that in a second. We've talked about medical image diagnosis before. Also, text classification, thinking about whether something's opinion, editorial, fake news, gossip. Mentioned the Airbnb customer lifetime value before. How much is any given customer worth through their lifetime? That's incredibly important for businesses to be able to predict that for their customers. Housing prices, how much will a house sell for, given location, number of rooms, area. This is a very interesting example. Insurance payouts. If I take a photo of my car after an accident and send it through to my insurer, can they tell me how much they think will be paid out based on that imaging? This is a huge challenge facing insurers at the moment. A lot of great work on that. Okay, so I mentioned this before, but supervised learning needs labeled training data, and what I mean by that is it needs to learn from data which already says whether a customer churned or not. Just like us, like we learn from the world, then we make predictions based around what we've learned. Okay. So given a bunch of data which tells the algorithm whether a customer churned or not, the algorithm then can do its best to predict on unlabeled data. Okay, so that's really the main thrust of supervised learning there. But it's a really interesting question. How do you get labeled data? Okay, so you can get it from historical data. You can do an experiment to get labeled data. You can also crowdsource labeled data. So Facebook did this initially when they asked you to label where you are in a particular photo, and now they're having a lot of people label where they are. Now they're pretty good at telling you where you are. So we all did part of their job for them. Another really interesting example is reCAPTCHA. So we've all had to type in this crazy stuff, right? And what reCAPTCHA actually does is it knows the label for one of them. So it knows that this is Arch, but it won't know the other one, or vice versa. And what it's getting, it's crowdsourcing our ability to recognize this. So if it knew Arch and I got that right, then it will take whatever I type for this as one data point around that, and aggregate hundreds or thousands of what people respond to that. But reCAPTCHA actually was used to digitize a whole bunch of the New York Times articles successfully. Okay, so to labor the point, the goal is to learn from data for which the right output is known, so that we can make predictions on new data for which we don't know the output. Okay, so several caveats. Supervised learning won't make business decisions for you. So it won't tell you what to do if you predict a customer is likely to churn. On top of that, and we'll get to this when we talk about ethics, there is a huge trade-off between accuracy and model interpretability. And a model may perform really well, but you may not know why it's telling you what it's telling. And if we have algorithms that are, out there predicting whether someone gets a bank loan or not, and we can't tell them why they didn't get one, that's a huge problem, okay? So I also want to make clear, thinking about it won't make business decisions for you. I had a beautiful conversation on the podcast with Renee Teat, who's a data scientist and data science educator, about how data science actually works. And this is one of her slides, which makes clear that data science doesn't actually answer questions in a vacuum. We start with a business question. We need to get to a business answer, and we factor that through data science, okay? Turn the business question into a data question, answer it with a data answer, then factor that back into a business answer. I want to say one thing about deep learning. I'm going to demystify deep learning in a couple of slides. Essentially, deep learning is the type of machine learning, mostly supervised learning, that's inspired by neural networks, by neurons, where we have, a neuron that sends an electrical signal to another, etc. There've been a lot of successes in image data and natural language processing. So essentially, we have input into our model here, a whole bunch of stuff happens in the middle, and we have an output, a prediction, okay? And we'll have upcoming webinars on deep learning in particular, but I just wanted to make that clear that it's a type of machine learning, and it's not necessarily much more special than that. It's been incredibly successful in the large scale analysis of medical scans and facial recognition in photos. And it's also been great for text classification and topic modeling of texts. So Google Translate's error rate dropped approximately 60% when it shifted to deep learning. This is somehow detected Yoda and translated it into that. And once again, I sincerely apologize for the cuss words. I'll put that on Yoda and Google as opposed to myself. I'll pass the buck there. So look, we've actually hit the 44-minute mark. I'm going to spend a few minutes, if you bear with me, talking about data ethics, just because it's so incredibly important and a really burgeoning conversation in the space currently. But I'll spend just a few minutes on this, and then we'll dive into the questions, which I'm really excited about. So I mentioned this before, but this idea of model interpretability, okay? And also, any questions, please put them in go to webinar ASAP if you haven't already. So thinking about why a model makes the decisions it does. So the Compass recidivism risk score was used to predict whether someone will reoffend. And that prediction was then used to inform parole decisions. And ProPublica did a huge expose of this and demonstrated that it's biased against black people. So this is a huge challenge when thinking about fairness and ethics in data science. This is one of many examples. I'll urge you to check out Cathy O'Neill's book, Weapons of Math Destruction, for further. And another beautiful book that I'm currently reading called Automating Inequality. And it's about how a lot of algorithms out there are actually automating a lot of the inequality we already have in society. And there is kind of a coda to that, in that this isn't new necessarily. I mean, we have a lot of biases existing in society, but it is problematic to automate them and do it at scale as well, which is one of the biggest challenges. Cathy O'Neill is thinking about this. I mentioned before that, her new definition is data science doesn't just predict the future, it causes the future. And something she's working a lot at the moment is thinking about algorithmic audits. And along these lines, an ethical matrix in which the rows are the stakeholders and the columns are the concerns. So for the recidivism model, we have the court as a stakeholder, black defendants, white defendants, the public, North Point, who are the people who built the algorithm, and as concerns, we have efficiency, fairness, false positive, false negatives, and so forth. And so thinking about it in these terms, I think, is definitely a step in the right direction. Amoju Miller, who's a senior machine learning data scientist at GitHub, in this conversation about ethics we had on the podcast, said we need to have that ethical understanding. We need to have that training. We need to have something akin to a Hippocratic oath, as doctors do, of course. And there's a huge conversation happening now around whether we need to have an oath or a code of conduct or a checklist, for example. And Mike Lukides, Hilary Mason, and DJ Patel have written a series on this that you can check out. And they've actually there's a free Kindle book of this series put together. And if you search for them, you'll find it. And one of their pieces is called of Oaths and Checklists, and thinking about whether an oath is most appropriate or a checklist. And doctors, of course, have oaths. They also have checklists in the sense that, it's not necessarily part of the Hippocratic Oath, but a doctor knows to scrub their hands and wash and put gloves on before performing surgery. And thinking about kind of data hygiene in terms of a checklist for data scientists is incredibly interesting. There's an organization called Driven Data that's put together Dion, which is a tool that allows you to easily add an ethics checklist to your data science project. So I urge you to check that out. And there are a lot of resources on this. The Fairness, Accountability, and Transparency in Machine Learning group, otherwise known as FATML, is fantastic. Data and Society and AI Now are both doing a lot of research into these types of ethical questions. So I urge you to check all of these out. And I'd just like to say thank you all for joining. We've got time for questions now, and do get in touch with us. Let us know what you thought of the webinar. Tweet at me at Hugo Bown and tweet at DataCamp at DataCamp. Do tweet at both of us if possible. And I've now got a bunch of questions. This is very exciting. We have around 10 minutes for questions. The first question is from Isaac. Isaac has asked, what tools do you see as the future of data science in the short term and long term? Python, R, something else? In the short term, I think Python and R are definitely the best bet. I always also say SQL, learning how to, a lot of data exists in SQL databases, and learning, the basic SQL querying in order to get your data out will prove incredibly important. In terms of data wrangling, data visualization, this type of stuff, Python or R at the moment. In the long term, and in terms of choosing Python or R, in all honesty, I'd choose one and go with it, or try both out, see which you enjoy writing more and go with that. Both have some pros and cons, but in the end, they're both fantastic for data science. In the long term, that's an incredible question. In the long term, I think, whether data scientists actually exist as a profession, or it's a lot more specialized and everyone has data skills, is an open question. But let me put it this way. I think in 5 to 10 years, far more people will be using machine learning as a service rather than coding themselves in Python or R. And that isn't to say data scientists. Data scientists will always be coding, or data analysts in a lot of ways. But you can imagine that, you work for a company doing BI and need some basic machine learning modeling, that you pay for a service that, or you're on a marketing team that needs to make certain predictions. You pay for a service that takes in your data, and you've got a graphical user interface to do that. And we're going to see a lot more of that. Okay, so let's see. We have a great question from Beth, which is there a minimum size of a data set where data science techniques aren't useful because of non-parametric distributions, or just things being too difficult to predict without additional data? So there are rules of thumb, right? All of which break down in certain cases. So my background's in um, mathematical biology and like cell biophysics essentially, and I'd see people come and report the mean of a data set or the average with 3 data points, and that's definitely way too small. You know, n is equal to 6 is probably still very small, but people do that. But I would say if you want to report the mean and you make basic assumptions, n is equal to 10 is probably okay. But I do think that, one example is thinking about deep learning, where you probably need to develop a relatively basic algorithm that performs kind of well to classify dogs from cats in images, for example. You need on the order of like 2,000, one to 2,000 images. That's pretty standard. I'll answer the question more generally now, in that essentially the more data you have, the less assumptions you need to make about it. So if you have like 1,000 or 2,000 data points and can see what the distribution looks like, you don't really need to make assumptions about the distribution. Whereas if you only have a few data points, you need to make a whole bunch of assumptions to say anything. And that's a very general answer to your question. Max had a really good question, which is, what online courses, books, blogs, podcasts do you recommend to advance on data science when coming from a non-tech background? I honestly think I'm going to answer this in a roundabout way. The best thing you can do is get involved in communities. And what I mean by that is go to conferences such as, there are PyData conferences all over Europe and the US. ODSC has incredible and affordable conferences where you get to learn a lot, but you get to meet a lot of people and see what's happening currently. In terms of online courses, let me think. So the way I'll answer that is there are a lot of resources online in Jupyter Notebooks. So there's a website which is a gallery of interesting Jupyter Notebooks, which has a huge amount of domain-specific stuff, and a lot of them can be launched in something called Binder. There are other examples, but essentially what it does is it takes a Jupyter Notebook from GitHub, for example, and you can then interact with it, and they launch a server where you can actually enter code there. One example of this is Jake Vanderplas's data. I'm sorry, the names escape me. It's the Python Data Science Handbook, and if you look that up on GitHub, you'll find a way to play with that interactively. And in all honesty, there are so many books out there. If you want to think about machine learning in R, for example, Max Kuhn's Applied Predictive Modeling is incredible. If you want to think about deep learning, Francois Chollet's deep learning in Python book, and he has a deep learning in R that he co-wrote with JJ Allaire now, is also fantastic. I mentioned Renee Teep before, Becoming a Data Scientist. Her website actually has a huge amount of incredible resources there. And so I'll move on to another question. Trey has a great question. Are the results of a neural network model, so deep learning model, interpretable at all? The short answer is no. So deep learning is very famous or notorious or infamous for being black box models. But there are techniques that allow us to make them interpretable. I actually discussed this on the podcast several times. So what you do is you can look around a particular point and form a related model that will be interpretable, and you'll do that reducing the accuracy or how well the model performs, but it will make it interpretable. One example is called LIME, so that's locally interpretable model agnostic. I think I'd urge you to check out. And I wonder if there's anything more I want to say about that. Yeah, I think the real challenge is there's always a trade-off between interpretability and accuracy, how well it performs. So generally, you can do your best to make it somewhat interpretable at the expense of how well it performs. So Richard has a great question. Tips for anonymizing data to ensure it can't be de-anonymized. This is such a great question, and I don't have a good answer to that. The best answer I think is look at the work done by Apple. I think Apple's probably the best example of work for at least pseudo anonymization, and they've published a series of papers on it. But it is an unsolved problem. And if you think, for example, also, yeah, the work of Cynthia Dwork as well. She's got several very interesting papers on this stuff. Let me think. Yeah, if you think about it though, let's say your data is, in inverted commas, you think it's anonymized, but then there's some other data which then can inform it to de-anonymize it. And that's something data scientists do a lot. They take data from different sources and join them or aggregate them, these types of things, to extract more information. And so anonymization is a very difficult task. Beth has a question. How do we do this better? I'm not sure what that refers to, but what forums should we have for discussion of data ethics? I think the forums, the places I mentioned, chatting with these people, FatML, AI Now, Data and Society, Twitter is an incredible place to have these types of conversations. But these conversations need to happen, from within the community of data scientists, from grassroots organizations, from stakeholders, from paying customers, from legislators as well. And I think the more we the more we have this conversation at different levels, the better we will be. Eddie has a great question. Considering data literacy is such an important thing to learn on a datafied society, how do you become data literate without having to learn statistics, coding, or data science? That's an incredible question, and because it's what we need to do essentially. That's why it's one of the reasons it's such a good question, Eddie. And the current answer is that there's not a great solution, but that's why I'm starting to give webinars like this, and this is something we're thinking about a lot at DataCamp. And we do have in the pipeline a bunch of non-coding courses to promote data literacy and these types of things, particularly for managers and C-level as well. So this is relatively unexplored terrain, Eddie, and something we're working on very passionately and wholeheartedly at DataCamp. So the short answer is watch this space, because we got a lot more of this stuff coming at you. And I think that's a great place to end the webinar, actually. So do feel free to reach out. Let us know how your experience was. And this video will be available afterwards as well, if you'd like to share with any of your colleagues and or friends. All right, thanks once again, and I'll see you next time.